Good evening, everyone, and welcome to this lecture. We are dealing with electrostatics, and this is lecture number 11, 12, I think. 12, yes. In the last lecture, we had seen the concept of Gauss law, and I think I had given you a question wherein you had to find out the electric field due to an thin sheet. A non-conducting sheet of thickness D. Anyone got the answer for this one? This was the question I think I discussed, and I told you that this is the last question for Gauss law to cover it once and for all. Anyone got the answer for this one? Did anyone try? How many of you tried? Only one. Oh, 4, 5. Okay. We tried. Anyone got the answer? The answer is already there. I already showed you the answer. The answer is already there. How did you try? Anyone can tell me what was the question and how it has to be done. So I will draw the diagram for you, and I will hope that looking at the diagram, probably you would be able to solve the question. Remember, in this question, the everything is the diagram. So this is your infinite sheet. The thickness of this sheet is given as D. Okay, the sheet is infinite in 2 dimensions. Right now, if I talk about the dimensions, this is x-axis, this is y-axis, and this is your z-axis. So along y-axis, it is not infinite. It has a thickness D. It is infinite along x-axis, and it is infinite along z-axis. So it exists infinitely long like this. Now, what you had to do or calculate, if you take this central plane, this is the central plane, you have to find out the electric field at a distance x from this central plane, somewhere here. Somewhere here, you have to find out the electric field. At this point P, whose distance from this central plane is x. This is the diagram that you were supposed to draw and find out. Anyone could do it now. I've drawn the diagram for you. Once you know the diagram, probably you have a better chance of doing it. So I'll still give you 2 minutes to try and do it now that you have a diagram in front of you. 2 minutes I'll give you still.
Sir, assume the Gaussian surface as cylinder.
Since this is a infinite sheet, take the Gaussian surface not as a cylinder but as a small sheet only. Don't have to take it as a cylinder. You have to take it. See, this is the infinite sheet. This is the question. It is infinite in this dimension and it is infinite in this dimension. It has a thickness D. It has a thickness D. This is the thickness D. So what you do, you can take a Gaussian surface like this. This is your Gaussian surface. Sheet type Gaussian surface you can take. And try and manage it out. I'll give you 2 minutes.
I did it by assuming Gaussian surface as cylinder, sir. I got the answer.
Cylinder is not the correct assumption here because See, you can get answers by absolutely wrong concepts. The Gaussian surface cannot be a cylinder here. It cannot be a cylinder here because of the simple reason that the electric field will not be same at all the points. So you cannot take Gaussian surface as a cylinder here in this question. It's a absolutely wrong concept. You do wrong things with a wrong concept. Two wrongs may make a right. That is not the correct way to do it. You should take, and I will draw the Gaussian surface if that is the case. The Gaussian surface will look like this for this particular question. I will enclose a Gaussian surface like this. This is, oops. This is my Gaussian surface. Oh, you can't see it. This is my Gaussian surface. This is my Gaussian surface that you have to take. I will take it infinite in this dimension. I can also take it infinite in this dimension, but why to make things complicated? I can take the length of this Gaussian surface as L. I can also take it infinite in this dimension. Doesn't matter. The concept remains the same. So this is a Gaussian surface. Electric field for this Gaussian surface will be constant at the point P, not for a cylinder. Cylinder is the wrong Gaussian surface. So now try. Two minutes you have at the max. One more minute. Remember why we are doing this. You are not expected to get this question in a JEE Main, but you can get a question of this type in JEE Advanced. They can create a hole, a spherical hole in this Gaussian surface as well. So this becomes a question of the type that came in that year where they had a cylinder with a spherical hole. You can create a spherical hole in this and then they can ask you. And that is why we are doing this, so that we understand how it is done. Nothing else. There is no reason for that other than this. So you must understand how it takes and what type of questions can be made here. Yes, your time is getting over pretty soon. Okay, let me do it. So this is the Gaussian surface that I have taken. Now, this Gaussian surface includes a charge. And how much charge will come in this Gaussian surface is how much charge will come in this volume. How much charge will come in this volume. Anyways. Now, at this Gaussian surface is like this. But all the points on this electric field is going to go upwards for the upper half, and electric field is going to go downwards for the lower half. And the angle between area and electric field will be 0. For all these side white portion, when I say side portion, the side portion is this. Electric field is going to be variable for this side portion, but the angle between electric field and your area vector would be 90. So whenever I am trying to find out the flux through this Gaussian surface, I only have to find out the flux through this surface and this surface. Do we understand this? Do we understand this? Yes or no? Flux through upper surface and flux through lower surface is what you must understand. The flux through these two sides. If this thing comes handy. This is my Gaussian surface. Electric field will go like this. For upper half, for lower half, it will go like this. For this side and this side, the electric field will go like this, and area vector would be perpendicular. So you will get angle as 90. So you don't have to calculate the flux through this one. Now, once you understand this, everything becomes pretty damn simple. So how do you find out the flux? To calculate the flux, you have to find out what is the surface area of that Gaussian surface you have created. Remember, it is infinite in this dimension. It is very large in this dimension. I have taken the length as L. Let me take this infinite length. Let me take some value. Let me take this as D. Now, if I take this as D, the area of the surface, the length is D and the width is L. So area of the surface becomes D multiplied by L. Do we understand this? So if I find out the Gaussian flux through this surface, it will be E multiplied by D multiplied by L, the flux to the upper half and the flux to the lower half. So it gets multiplied twice. Flux to the upper half and flux to the lower half. That must be equal to how much charge is coming in this Gaussian surface that I have created. The charge coming in this Gaussian surface would be equal to the volume of this Gaussian surface multiplied by rho. So rho, what is the volume of this Gaussian surface? The area of this Gaussian surface is D into L, and the width of this Gaussian surface is 2 times x. X on the upside, x on the downside, divided by your favorite epsilon naught. What is going to happen is your D into L and D into L will get cancelled. Your 2 and 2 will get cancelled, and you will end up with the answer rho x by epsilon naught. And it will be going on the upper side perpendicularly like this, and on the lower side perpendicularly like this. Do we understand this, or this has gone above our head saying bye bye? Do we understand this, how it has done, and why
Yes,
I
sir.
cannot create a cylindrical Gaussian surface? Because for all those points on the cylinder, electric field is not going to be same. So I cannot create a cylindrical Gaussian surface. This is how it is done. Do we understand this?
Yes, sir.
This was for point inside. Can you tell me what is the electric field outside? What will be the electric field outside for outside points? This was for electric field inside. Now taking the hint from electric field inside and how I've created the Gaussian surface, can you tell me what will be the formula for outside? Once you derive it, remember it for the rest of your life, at least till the day you are giving your JEE. Because if you have to do it again in the examination hall, whatever we are doing now is a waste. The only reason we are doing it now is that once you do it now, you don't have to do it in the examination hall. We have time now to do it. We won't have time later on. Yes, outside points. I'll give you 1 minute to tell me the answer for the outside point. Yes, do we have an answer to the outside points? Or shall I do it? For the outside points, what will be the difference? I'll again create a Gaussian surface. The only thing is x will be more than d by 2. So it will come outside.
Sir,
Yes, beta.
rho x by 2 epsilon naught, sir. Rho L by 2 epsilon naught.
Rho L by, there is
2
no
epsilon
L.
naught.
There is no L here. There is no L here.
X, sir.
Okay, I'll do it. For any point outside, let me do it with the blue thing. Otherwise, I'll have to draw the entire diagram again. So this blue thing now will look like this. This blue thing now will look like this. And I hope you understand this blue thing is my new Gaussian surface. This blue thing is my new Gaussian surface. And the distance of this from the central plane is x. Again, I create that same Gaussian surface. Ding, 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 ding. Now remember, I'm talking about point outside. Now, if I again calculate the flux, again I have to calculate the flux to the upper half and the lower half. And the answer still remains 2 times E into D into L. Do we understand this? Oh, I've taken everything as D. Okay, that is a problem. This is D. I should not take this as Z. D. Let me change it. Otherwise, it will create confusion. Let me take this is L. Let me take this as B. Breadth, whatever. So here it should not be D into L. It should be B into L. Here it should not be D into L. It should be B into L. Okay, now it is correct. Okay, I'm taking it for point outside. I forgot that D was the thickness of the slab. Now, the flux, the outside surface area is still B multiplied by L. So the flux still remains 2 times E into B into L. But when I look for the enclosed charge is not enclosed up till the point X. The enclosed charge will only be coming in this green zone. This is the only charge that has been enclosed by this. And as you can see, it has got nothing to do with the length X, because charge only comes in the sheet, and the sheet has a thickness of D. So what is the charge enclosed? Rho is the density multiplied by volume. The volume is area multiplied by thickness. Area still remains B into L. Area still remains B into L, but the thickness of this sheet, I can only take the thickness of this sheet. It is simply equal to D divided by epsilon naught. And when I cancel this stuff, I end up with the electric field, and electric field comes like this, rho D by 2 epsilon naught. That means this is constant. And if you look very closely, this rho into D is our old friend. Who was our old friend? Rho into D, old friend. Sigma by 2 epsilon naught. It becomes an infinite sheet for outside points. And it creates a uniform electric field. That is the point that I wanted to tell you. That for this sheet, outside points, it just acts like an infinite sheet. But for inside points, it is different. Do we understand? Or it has gone above our head saying bye-bye? Sir, enough?
Understood, sir.
Boys, have you understood this?
Understood, sir.
So remember this. And that is the reason I gave you this question, so that you understand. And the graph of this thing is pretty good. If you plot a graph, and remember all these graphs, why I'm plotting every time, because these graphs are quite popular these days. How does the graph between electric field and X looks like? They might not ask you the values. They might just give you the 4 graphs. What is the electric field? How does the graph look like from the central plane? How does the graph look like from the central plane?
Straight line, sir.
Red line, sir? Straight line, sir. Yeah, straight line. So inside, it is a straight line like this, directly proportional to X. And then it becomes a straight line like this. And at the peak on the surface, it becomes same rho D by 2 epsilon naught. So remember this. We have done it once, and I hope that we don't need to do it again, because if we have to do it again in the examination hall, it is a waste of what we have done today in the class. I'll give you a minute to note it down. Note it down, draw the diagram, keep it somewhere safe. Remember, you don't have enough time to cover everything twice or thrice. Electrostatics, we are only doing it once. That should be good enough for always. Note it down. I'll give you a minute.
Done, sir.
Completed, sir.
Everyone, good. Remember this. You will not get chance to. We will not get chance to repeat this. Okay. Having said that, we are done with this. Let us move ahead and move on to the next topic, which is electrostatic potential energy. Electrostatic potential energy. We have dealt with one type of potential energy before, I think. That was gravitational potential energy. Yes or no? Do we remember anything about that?
Yes, sir.
Gravitational potential energy. So when we are doing electrostatic potential energy, we are also doing gravitational potential energy together. Your chapter on gravitation I will do once we are done with this electrostatics, and then side by side in the Sunday wala class I will finish your gravitation. together. Remember, whatever we have done in electrostatics, the same thing we have to do in gravitation. Apart from just that gravitation G wala, apart from that flying that satellite wala thing, otherwise everything is exactly same. No, everything is same. Electrostatic potential energy. Now, what do you mean by this electrostatic potential energy? Yes, can anyone tell me? So this is electrostatic potential energy. What do you mean by this electrostatic potential energy? If I take out this word electrostatic, it just becomes potential energy. So it could be gravitational potential energy, it could be spring potential energy, it could be electrostatic potential energy. These are the three types of energies that we are going to encounter in our discussion. What do you mean by electrostatic potential energy? Let me start again. Yes. Anyone, any idea? No? Have you heard about that conservative force? Have you heard about conservative force?
Yes, sir.
What is the conservative force? See, I'm trying to cover it in all the ways as possible because I know this conservative force comes in the chapter on work, power, and energy. This also comes in the chapter on gravitation.
Path independent, sir.
This also comes here in this conservative force. A conservative force is a force, yes, that is very correct. This is a path independent force. Path independent force. What do you mean by path independent force? What do you mean by a path independent force?
That's not
The work done by the particle in any path is same.
depend upon the path.
See, if you understand something, you have to speak it in the correct way. If you say the thing in the wrong way, that means you have not understood it at all. Right? Don't have to say it in English, but yeah, if it's talking Telugu, I may not be able to understand it. But you have to say it in the correct way. And I'm going to write it in English. You don't have to write it in English. You can write in any language that you feel comfortable. Path independent force means the work done by a particle. No. Work done by or against this force. Work done by this force, not any particle. Work done by this force or work done by something against this force. Work done by or against is not dependent on path. It's not dependent on path. It does not depend on path. What does that mean? It does not depend on path. What does that mean? So if let me draw ding as well, so that I can take the analogy back to something else. If I move a particle from point A to point B in any path, ting, 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 path number 1, ting, 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 path number 2, or ting, 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 path number 3. The work done by this force that we are talking about does not depend on path. It only depends on what was the initial position and what is the final position. Do we understand this? So work done in path 1 or part 2 or part 3 done by this force will be same. That is what I mean by a path independent force or a conservative force. Work done by this force will be same along any path. Do we understand this?
Yes, sir.
Does this path independent remind you of something that we have just now done? When I say just now, maybe 2 days before or somewhere around 2 days or 3 days before. Path independent. Does not depend on path. Huh? No, sir. You're not done anything. 2 days before we were studying Gauss law.
Internal energies.
Internal energy. Yes, we were studying internal energy 2 days before. Internal energy, state variable, does not depend on path. Same here. Does not depend on path. Internal energy, potential energy, internal energy, potential energy. Internal energy is also a path function. It's not a path function. It only depends on the initial and the final position. So you don't have to see where this. So once you understand conservative force, you understand potential energy. You understand internal energy as well. So you can take the analogy back together, and that is the reason I'm teaching thermodynamics with this. I can relate things. And remember, when this heat transfer comes, we will again relate it to something else. We will not be able to go so far ahead by the next week, probably. Okay. Path independent, it does not depend on path. So you go from any point 1 to any point A to any point B, the work done does not depend on path. One more thing. What is the second way in which you can do the same thing, in which you can say the same thing? This is one statement. I can say this statement in a different way. How? Thinking. See, 2 days before I told you that. 2 days before. 2 days before. Work done by this conservative force in a closed path. Closed path or a closed loop is how much?
0.
Does it remind you of something?
NCDT, sir.
NCDP? What NCDP? Work done by this conservative force in a closed loop is 0. Does it remind you of something? Cyclic process. Start from one point, come back to the same point. Change in internal energy is 0. Work done is 0 by conservative force. Same concept. That's why I've drawn the graph. I've just drawn X and Y. I could have drawn PV. Same thing. State function. P and V tells us the state of the gas. X and Y are telling us the position of the point. Same thing. Do we understand this or bye-bye?
Understanding.
When I do that PV graph, I also tell you PV state variables. You change anything, the state changes. This is same thing like coordinates X and Y. If you change X and Y, things change. Conservative force. Work done by a conservative force in a closed loop is 0. These are the two things that you must remember about a conservative force. A move in a closed path, it is 0. Now I can write this in a very dramatic way. How can I write this in a very dramatic way? This should again remind you of this. Work done by a conservative force in a closed loop is equal to 0. That means integral of f dot dl over a closed loop is 0. Dot product. Dot product comes, yes. F dot dl or F dot dr is the work done, yes or no?
Sir.
Yes or no?
Yes, sir.
Integral of F dot dr is total work done, and I put a gola, it becomes a closed loop. I put a gola somewhere else also, na? Where I put a gola somewhere else also, na? You get golas in exam, I know, but apart from getting golas in physics in exam, I put a gola somewhere else also, na? This gola, this round. Where?
Gauss law, sir.
Gauss law. Closed surface it was. This is closed loop. Difference. What is the difference? Okay, we will understand the difference. So the work done by this force in a closed loop is going to be 0. Now, when I talk about conservative forces, 3 forces should come into your head. What are the 3 forces that should come into your head? Huh?
Gravitational force.
Gravitational force. Only one force. Yeah.
Spring force.
Gravitational force, spring force, and your electrostatic force. The work done by these forces in a closed path is going to be 0, and it does not depend on path. Everyone understands this? Yes or no?
Yes, sir.
Sir.
Okay, I was not planning to do this. You can't leave anything on chance. If I leave anything on chance and it comes and you are done. Now, the best example is gravitation force. So we'll try to go back into gravitational force, and I'll give you quick, because it may not be so easy to understand it from electrostatic point of view. So from gravitational point of view, it is very simple, because this question may come in gravitation, it may come here, it may come there. If I move this block from point A to point B, if I move it straight like this, or I move it straight like this, or I move it like this, the work done is going to be 0. The work done is going to be same against gravity. Yes or no?
Yes, sir.
Yes, sir.
Same thing. Now, in gravitation, what was happening was I was moving a mass. Gravitational force can move a mass. The work done by that gravitation force in moving that mass does not depend on path. Now, if I take the analogy from gravitation to electrostatics, what will be the analogy in electrostatics? Huh? Gravitational force can move a mass from one point to another. It can exert a force on a mass, and it can move a mass from one point to another. Here gravitational force is doing it, moving a mass from one point to another. The work done by this gravitational force does not depend on path. How can I take the analogy back to electrostatic force? Huh?
Charge.
What?
Charge.
Mass becomes charge, and the gravitational force becomes the electrostatic force. So the work done by electrostatic force in moving a charge is independent of path. Do we understand this? The work done by gravitational force in moving a mass is independent of path. The work done by electrostatic force in moving a charge is independent of the path. That is what you will write in your own language. Write it. That is what we call conservative forces. Work done by gravitational force in moving a mass is independent of path. Similarly, a work done by electrostatic force in moving a charge will be independent of the path in which it is moved. We understand this?
Yes, sir.
Okay, quick. We have noted this down. Remember, we are covering 3 chapters here. Whenever we were covering electrostatics, we are also covering the chapter of gravitation. Here we are also covering the chapter of work, power, and energy together, because now work and force is going to come. So work, power, energy is also. So we are doing 3 chapters simultaneously. Have you noted this down?
1 minute, sir.
Okay, let me know once you're done.
Gravity.
Done, sir.
Girls team, doing, sir.
Done, sir.
Okay, sir. So here we are, gravitational force. Example, you just have to write in your own language. You don't have to copy everything down from the whiteboard. Gravitational force, spring force, electrostatic force, conservative forces. Magnetic force between two magnetic poles. Remember, magnetic force between two magnetic poles is a conservative force. Force acting along the line joining the center of two bodies are called central forces. Electrostatic and gravitational force are central forces. All central forces are conservative no matter how they come. Remember this, central forces. These are the next word that you have to remember. Central forces are conservative forces. Central forces are those forces which act along the line joining the two bodies. Central forces. Central forces are conservative because in an exam, they can just use this term central forces. These two are central forces. Find out this, find out that. Remember, central forces are conservative forces. Note it down fast. Just note down the highlighted points in your language, nothing else we need. We don't need the entire Kahani here. We don't need the entire Ramayana here. We're only doing the Sundarkand. So we just remember the portion of Sundarkand, what happened. I don't remember what happened in Sundarkand. Sundarkand is one of the Kands of the Ramayana. So we must know who is Ram and what did he do. Who is Bhagwan Ram? What did he do? Have we noted it down? I hope you are paying attention to what I'm saying, bacha. You just have to note the important points, not everything. Note it down.
Yes, sir.
Now remember here, you have seen that every gravitation, electrostatic, magnetic force, spring force is conservative force. Every central force is a conservative force. One more thing, remember, every constant force is conservative. Every constant force is conservative. Every constant force is conservative. It does not depend on path. You don't have to worry about the path. Which path is going, don't worry. Conservative. You understand this? And again, I would be covering everything about this conservative force in a nutshell. Whatever we need, maybe in your 11th standard, maybe in your 12th standard, maybe in gravitation, maybe in electrostatics, doesn't matter. We will be trying to deal with them all. Have you noted this down?
Sir.
These are the properties of the conservative force in general. Now, again, I have told you all of these properties, but the same properties are written in different ways. So if a question comes, you must be able to understand that these are conservative force. The first point is work done by or against does not depend on the path. It only depends on the initial and final positions. The same thing is said in the second statement. The third statement is the reverse of that statement. If the work done does not depend on path, then the force is conservative. The fourth statement is the roundabout statement. Round trip is 0. Then the fifth statement is the reverse of that round statement. The sixth statement is the statement that we will be working on. The concept of potential energy exists only in the case of conservative forces. So wherever you have this concept of conservative forces, we have an energy coming there, and that energy is known as potential energy. And why will this energy come? We will see that. The work done by conservative forces is completely recoverable. If the conservative force does work in one path, in the next path, what will be recovered? Complete recoverability is an important aspect of the work of a conservative force. Okay, do we understand this? What have I said?
Yes, sir.
Note it down. Have you noted it down, everyone? Let me know once you are done, beta.
Done, sir.
Okay, sir. Now, here is a small question for you, sir. This is a pendulum, a string attached to a mass of bob M. Now, somehow I am moving it. I apply a constant force F. Remember, this force F, the blue force, is a constant force. I apply a constant force on this block. Remember, this F is constant. I apply a constant force on this block, and this question has come in a JEE. Apply this constant force on this block, and I move it from initial position, the bottom position, to that position. I have moved it horizontally, X, and I have moved it perpendicularly, height wise, H. There are three forces acting on this. Bob. What are the three forces?
Constant force, tension, and gravitational force.
Find the work done by all the three forces. Yes, do we have the answers? First thing first, what is the easiest one? All of them are easiest. What is the work done by tension of this string? Tension may not be same also. What is the work done by tension of this string? Huh? Are what is the work done by tension of this string? And the answer is no one knows this. Zero. Why it is zero? You move this block, tension is always perpendicular to the displacement of the block. The body is moving in a circular path, and tension is always towards the center. So the angle is 90 degrees, and therefore the work done by tension is zero. Do we understand this?
Yes, sir.
Okay, first thing done. Let us come to the second thing. What is the work done by the weight or gravity? What is the work done by G? G stands for gravity. Gravity of Earth that we are talking about. What is the work done by gravity?
MGH, sir.
How much?
Minus MGH.
Well done. Minus mgh. Simple things. You can answer this. What is the work done by the force F? Huh?
X square by 2, sir.
F into x square by 2. Is that? Or x square by 2? Which one? Huh?
F into x square by 2.
F into x square by 2.
2.
Everyone got the same answer? Yes or no? What is the dimension of work done? It is F into x, my dear friend. So your answer cannot be Fx square by 2, because then we are creating a new dimension for work, which is not possible in this universe. Open your eyes. This is a good universe to live in, 4% of which we see, which is beautiful. So let us remain in this universe and let us remain with the dimension of work, which is force and displacement, not squared. So let us remain in this universe and give an answer of this universe. Remember, you are in standard 12 now, and after 4 months, you are going to give your NEET. NEET.
Sir.
You are going to give your mains. You cannot give a dimensionally wrong answer. That is not accepted. There are dimensions are wrong. If you would have said fx by 2, I would have still understood. Okay, chalo, theek hai. Dimensionally, it is correct at least. Fx squared by 2, dimensionally wrong. Yes, try it again.
F into square.
Fx, sir.
F into x. That is the correct answer. F into x. As simple as that. F into x. That is the answer. Now that might be a akkar vakkar Bombay wo type ka guess, but can you tell me why is the answer F into x? And I hope it's not akkar vakkar Bombay wo 80 90 pure 100. Yes, why is the answer F into x?
Displacement is x.
Displacement is x and force is f, so answer is F into x. That is what I call akkar vakkar Bombay wo 80 90 pure 100.
Sir. Both are constant.
Both are constant means what? Both are constant. What both are constant? The answer is F into x. And it comes because of this term, force is constant. Now, as soon as the force becomes constant, the work done by this force does not depend on path.
Integration of f into dx, sir.
Yes, beta?
Integration of f into dx.
Integration. So let me complete what I was saying. This force is constant. Try to understand the concept of a conservative force, my dear friends. That is remember, in JEE, hardly you will get a question where you actually need to integrate it, because that integration may not be so easy and you might get trapped in that integral part. This force is a constant force. The work done by this force, dear friends, does not depend on what?
Path.
It does not depend on path. And let me draw a bigger diagram, and let us only concentrate on this force. And then you will try to understand what has happened here. This F, and that is why I said understand the meaning of conservative force, because we are going to deal with these forces. This F is a conservative force. The work done by this force does not depend on path. So even though this particle is going in a circular path, and if I try to find out the work done in the circular path, yes, my dear friend, you have to use that integration thing. But again, there will be angles and thetas and all this coming, and you'll be wasting around 4 or 5 minutes of your time in calculating that integral. And maybe at the end of the integral, you will end up with the wrong answer. If it does not depend on path, we understand this. Choose the easiest path. And what is the easiest path? The easiest path would be, I go straight, ding, 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 ding. And then I go ping, 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 ping. I will go in this path. This is the easiest path. And in this easiest path, I can easily find out the work done by this force. because I just have to find out the work done from A to B. From B to C, the work done is 0 because force is going to be perpendicular to your motion displacement. You will say, sir, the thing is moving in a circular path, but the force is conservative. It does not depend on path. So I first move horizontally, then I move vertically to get to the desired point. And when I move horizontally, the displacement is x, force is F, it is constant, angle is same. The work done is simply F into x in this path, and in this path, the work done is 0. So in any path, the work done from A to C has to be F into x, and that is the answer, my dear friend. You understand this, yes or no?
Yes, sir.
Now, the simpler way of doing this is, if you turn this diagram by 90 degrees, if you turn this diagram by 90 degrees, your F becomes your gravitational force. If I turn the diagram by 90 degrees, like this, the diagram looks like this. Ting, 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 ting. Your force F is here, and you move the object from here to here. This distance is given as x. Gravity is constant. Force F is also constant. Work done is F into x. So you could have understood it this way. You could have understood it this way. The way of doing that integral, you will get caught in that integral because you will do a mistake in that integral. And that is not what the conceptual understanding is. Do we understand this?
Yes, sir.
Whenever you see a constant force, don't worry about the path, because in any path that you go, you will end up with the same result. So be wise and choose the easiest path to go. An easiest path is always you move along the force and you move perpendicular to the force. Along the force, perpendicular to the force. Along the force, work done is F into x. If it's in the same direction, it is positive. If it is in the opposite direction, it is negative. Perpendicular to the force, it is always in the 0. Choose the easiest path. Do we understand this? Everyone?
Yes, sir.
Work done is 0 in the work done is F into x. This is how you can calculate the work done by any conservative force. It does not depend on path. Okay, we understand this?
Yes, sir.
So I will keep it up till here. I don't want to get into a complicated integral question that does not serve any purpose. The purpose has been solved up till here. Now we understand that this work done by this conservative force does not depend on path. It only depends on what was your initial position and what is your final position. It does not depend on path, and therefore I can create this concept of a term which is known as potential energy. From this conservative force comes this concept of potential energy. Now, what do you mean by this potential energy? Or in this particular case, I am going to call it electrostatic potential energy. In case of gravitation, you will call it gravitational potential energy. In case of spring, you will call it spring potential energy. Let us write the heading electrostatic potential energy. Electrostatic PE. Electrostatic potential energy. We are going to define this potential energy by U. U stands for energy. Here we are dealing with electrostatic, so we'll call it U as electrostatic potential energy. In gravitation, we call U as gravitational potential energy. In spring, we'll call U as spring potential energy. Now, since this gravitational force is a conservative force, work done does not depend on path. So instead of calling it as work done from here to here, I can call it by the concept of electrostatic potential energy. So how do I define this electrostatic potential energy? This definition is important. The definition of electrostatic potential energy is like this, and I will just write it in this form and then I will say how it is said. Delta U A to B is equal to delta W, negative of delta W A to B conservative force. This is the definition of electrostatic potential energy. Now, can anyone tell me in words how will I say this? I've written the mathematical expression for it, and I want someone of you to tell me how do I speak. Now, remember when I'm talking about this, I'm assuming what? I'm assuming that there are 2 points A and B. There are 2 points A and B, and I'm moving something. If it is a gravitational force, I am moving a mass. If it is electrostatic force, I am moving a charge. We understand this? Yes or no? So I'm moving something, mass or a charge, depending on which energy I'm talking about. I'm moving it from here to here along any path. Let us say I've taken this path. Yes. Can now anyone explain what I've written? Yes. Try. I mean, right and wrong are just concept in the head. Important thing is to understand. What does delta stand for? I've used this delta many times. What does delta stand for?
Change.
Change. Well done. Change is always final minus initial. So delta is change. Now, once you understand delta is change, you can just tell me the definition of the entire thing. Yes. What is the... So change in this case electrostatic, change in electrostatic potential energy in moving what I'm going to move.
Charge particles.
Moving a charge from a point. From where to where I'm moving it? From a point A to a point B. In where this charge would be placed. Remember, who is going to move this charge? Who is going to move this charge? Huh? Hey, who is going to move the charge?
Electrostatic force.
So it has to be in an electrostatic field, otherwise it will not move. Yes or no? Huh? So change in electrostatic potential energy in moving a charge from point A to point B in an electrostatic field is equal to what? Is equal to negative of the work done by electrostatic force. Electrostatic force is going to move the charge from point A to point B. The change in electrostatic potential energy is negative of the work done by this force. Do we understand this? That is the best way in which I can define this, or it is defined. And whenever I talk about change in electrostatic potential energy, it will be equal to final energy UB minus initial energy UA. So basically what I am saying here is this. Remember this, don't forget this. So basically what I am saying here is UB minus UA, electrostatic potential energy at point B minus electrostatic potential energy at point A is negative of work done from A to B by that conservative force. If it is electrostatic force, it is electrostatic work done. If it is gravitational force, it is gravitational work done. Do you understand this?
Yes, sir.
Now, instead of writing it in this way, you can write it in the reverse way. When I write it in the reverse way, UB minus UA becomes UA minus UB. And that negative side goes there. So it becomes positive of the work done. So you can also write it like this. UA minus UB is work done by the conservative force in moving the charge from A to B. Do we understand this?
Sir.
Okay. Now what you got to remember is very important point. Absolute value of electrostatic potential energy is not defined. Remember, as Einstein said, everything in the universe is relative. Nothing in the universe is absolute. No motion is absolute, no rest is absolute. It all depends on your reference frame. Similarly, this electrostatic potential energy is also not absolute. It cannot be defined in absolute sense. So the absolute value of electrostatic potential energy is not defined. Then what is defined? Only change. When I say change, it is final minus initial, or difference, initial minus final. Difference of electrostatic potential energy is defined. Now remember, whenever you had done any question in work, power and energy, you had one ground, and when you had a block of mass m at a height h, you had said that the gravitational potential energy of this body is mgh. Yes or no?
Yes, sir.
In that case, you had taken the gravitational potential energy of Earth as 0. Yes or no?
Yes, sir.
So this Earth becomes your reference frame. If you take the gravitational potential energy of Earth as 0, then you can say any point at a height h becomes plus mgh. Any point below the surface at a height h becomes minus mgh. But for that, you must define where is your 0. You have taken 0 on the surface of Earth. Do we understand this? That
Yes, sir.
means absolute value of gravitational potential energy or absolute value of electrostatic potential energy is not defined. What is defined is only the change or the difference between 2 points. So if you have to define the absolute value of electrostatic potential energy, you will have to find a point whose energy can be taken as 0. Up till now, in the chapter on work, power and energy, we were dealing with gravitational potential energy, and we had taken the surface of Earth as 0. Yes or no? But the
Yes, sir.
surface of Earth is actually not 0. To find this 0 of gravitational potential energy or electrostatic potential energy is an impossible task. You cannot find out a point where this can be taken as 0. But in most of the cases, if you go very far away from Earth, that is, you go at a point infinite distance from Earth, and again, what happens at infinity, no one knows. You can take, for all practical purposes, the gravitational potential energy at infinity to be 0. Do we understand this?
Yes, sir.
So if you take the gravitational potential energy at infinity to be 0, then only you can define the gravitational potential energies of different points. Do we understand this? But again, this gravitational potential energy at infinity cannot be taken in 2 or 3 cases. We will come across those cases in the next class. For all practical purposes, in most of the cases, you can write in most of the cases, energy at infinity is taken as 0. And if you take that energy as 0, then you can define the potential energy of any point in space. But in some cases, even that point cannot be taken as 0. We will see those cases, and we will see how will you define or how will you find out the gravitational potential energy in the next class. So I'll wind up this class here at this point. Do you have any doubts? Please ask me. We have started with electrostatic potential energy. In the next class, we'll move on with the next term, electrostatic potential, and then we will deal with some problems on the same. Take care. Have a nice day. God bless all of you. Bye-bye.
Thank you, sir. Bye.